Hello there, this is Hans Forschner with Navcon Engineering Network. This video discusses source directivity. If a point source is defined in the SoundPLAN Geo-Database, the default assumption is that the source is omnidirectional, radiates in all directions. The omnidirectional assumption is applied for the entire frequency range of the source. Obviously, that is a simplification, but for a lot of projects, that is adequate. But there are situations where simplifications are not good enough, and in those situations we need to make changes, consider how a source radiates or how it, how the radiation pattern is changed. Before I get into the 2D and 3D directivity setup and how you apply it, I'd like to discuss what is directivity and what is the source radiation factor, K omega or Q-factor. So here we have the radiation pattern of a sound source, and of course that could be, in some cases, that could be a loudspeaker, or it could be a stack, so we'll get into that in a little bit. So where the radiation is fairly complex. So we have increases in some direction, significantly increases in some direction. It's very inefficient in other directions. So what we have in terms of if you have a source close to a reflective surface or the ground, so if your source is relatively high, so here an example, point source up here, and it radiates in all directions. That is, for example, for low frequency, the stack opening that is elevated. The directivity is basically omnidirectional. It's in all directions the same. So wavelengths are pretty long. So we can assume an omnidirectional source. And in that case, the source radiates in a 4 pi r² space. If you look at the 4 pi, 10 log of 4 pi is 11 decibels. So when you predict the pressure level from the sound power, then of course you subtract the 11 decibels plus 20 log of the distance. So the spherical propagation is also considered a Q factor of 1, which means if we take the Q of 1, it's 0 decibels. So again, we have here the 11 decibels and the Q factor of 0. That's basically the correction to the full sphere. Now, if we have the point source directly on the ground, then the propagation, of course, is in 2 pi, in a half sphere. So we have the same, assuming the same source, we have the same energy radiating away, and of course the sphere cannot radiate in the full sphere. Anything that goes to the bottom, to the ground, is getting reflected upwards, assuming it's a reflective ground. So here we have the situation that the propagation can only go into the half sphere. So here we have 10 log of 2 pi, so that's 8 decibels. If we compare that, again, here we have a Q factor of 2, so that's basically representing the half. So 1/2, and the Q factor of 2 is 3 decibels. So here this is the difference between 11 and 8 decibels. So we have an increase. So if we have the same source, power level, the same distance to that point source on that sphere, so we have an increase from this point to this point by approximately 3 decibels, because the energy has to go into that half sphere. Now we put that point source in a 2-dimensional corner on the ground next to a wall. Then of course the radiation can only go into a quarter sphere. So here again, the surface area is pi r², 10 log of pi in this case is 5 dB, the Q factor of 4, the 10 log of 4 is 6 decibels. So compared to the full spherical radiation, we have an increase of 6 decibels if you have a source that is close to the ground, close to a wall. And so again, we assume with the same power level, we would get a 6 dB increase in terms of the level at the same distance away. And you can continue with that. So if you have an 8th sphere, so 2 vertical walls on the ground, so here we have a half a pi, Q factor is 8, the log of 8 is 9 decibels. So here again, the comparison between 2 dB and 11 dB, it's 9 dB increase. So again, at the same distance away from the source, we would get a 9 dB higher sound pressure level, or intensity level, if you want to say that. So again, these are the different Q factors, K omegas, and most standards, or like if you talk about ISO 9613, they assume again either spherical propagation. If the source is close to the ground, then the correction that we have here with the Q of 2 for the 3 dB for propagation a half sphere, a lot of that is done through recognizing what's the source height above ground and the receiver height above ground. That is for the simplified ground model. And then if you have the more detailed ground model, again, depends on the source height above ground, receiver height above ground, and it's basically considered as part of the ground correction. Now, in terms of the effects of walls, vertical walls, those corrections in terms of the comparison between half sphere to quarter sphere or eighth sphere, these are corrections that would be solved in SoundPLAN either through the reflection from the wall. So if you have a source in front of the wall, the program can either consider the reflection off the wall. So you have basically another path. So by having two sources, the direct and the reflected, you would get an increase of 3 decibels. Or you could assign to the source that is on the wall a K omega correction. That correction is typically automatically set by K omega of 3 decibels or 6 decibels, depending if you have a single vertical wall or if you have a two-dimensional corner like on the very right, where you have basically two walls radiating into an 8th sphere. So again, those are some of the corrections that you have available. So again, that's not really a directivity. That's basically a change of the radiation just due to the geometry of the source being off the ground, on the ground, next to a wall, or close to a three-dimensional wall or three-dimensional corner. Now, when you for any kind of manufacturing aspects, you have, of course, the exhaust stacks or any type of exhaust pipe that sticks out of the side of a building. We can have walls, we can have roofs, we can have openings in walls and roofs where you have a certain source that is radiating away from those surfaces. Then extreme directivities could be from loudspeakers, a bass loudspeaker, tweeter, so that could be something to model in SoundPLAN. Then we have firearms, rifles, guns, cannons, or human voice. If you have a source that represents a person, there's of course a lot of directionality with screaming or someone talking, where the body by itself offers certain shielding and also radiation patterns. So these are all different examples of where it's interesting to define a more detailed directivity of the source. Now the sources or source directivities are defined in the library. So let me open up the library here. I can go up in the library section, and here is the directivity. In this example project that I have a couple of already existing directivity patterns. And so again, in the system library, we have a whole section of different directivities that come with the software. So some of the newer ones are like Stack Directivity with different diameter stacks. And then here we have a directivity pattern that is frequency dependent. So let me go maybe a little bit a higher frequency so we can kind of see this. So here we have the directivity. This is scaled from +9 to -9. Here we can, with a right click, we can show the grid. So here we can get a grid visualization of the directivity. We can also turn on some planes, so that's kind of a little bit easier to see what is right and left, up and down, and so on. All right. And then, of course, here this is then for all kinds of frequencies, all the way to 16 kilohertz. With the wheel on the mouse, we can zoom in, zoom out. And with the control and the left mouse, we can basically rotate and get the direction from, or look at the directivity from all kinds of directions. Now, in terms of what is a positive value and what is a negative value, so positive value means in those directions there is more significant radiation to the average directivity of, or the average omnidirectional radiation of the source. So we use as a baseline the omnidirectional source. Positive values means we are increasing the radiation in those directions, and in this case we have a source that is rotational, symmetric. So this is the definition here in this system library. So this is a rotational symmetric source input, in this case every 10 degrees, and in third octaves from 25 Hertz to 20 kilohertz. So these are some of the default definitions for the source. Then we can go to some of the other sources and can see the variations of that. Now this one is fairly, just because it's omnidirectional, the values are the same for all angles. So if we look at the raw data, we have basically the data from 0 to 180 degrees. So if we look at that, it's basically from down here up here, and then it rotates that slice 360 degrees around the sphere, right? So again, here are the raw data for the different frequencies, and then in terms of the values for each angle. So here we see one of these slices. So here in this case for 25 Hertz, 31, 40, 50 Hertz, and then all the other angles are basically a duplicate. So whatever we change in this slice, it will be duplicated to all of those angles. All right. Now, if we have some sort of a line array, then we have a little bit of a different situation. So let me look at the details of, for example, this 2 kilohertz line array directivity. Here we have the 3D view, again -2 to -30 dB. Here on the right hand side we see the blue cross section, which is basically the horizontal slice through this directivity, and then the green line is the vertical slice through the line array. So this is a very directional source and fairly flat. So that's basically to direct the sound into a very specific area of the audience, for example. All right. Now, in terms of the settings, this is a full 3D input, and it's in 10-degree increments, in this case in octave bands from 63 to 8 kilohertz. Right. Now, if we're looking at the raw data, we have the data in this case for these octave bands, everything below 63 Hertz, and then 125 to 8 and over 8 kilohertz. With this, we actually have basically coordinates in Phi and Theta, and the program interpolates between those data points that we have here. All right. Then here, these are actually calculated in all for all the different frequencies, and so here we have again the rotational angles or elevation angles, and then here we have the horizontal angles. All right. So this is again in terms of the input with Phi and Theta. So Phi is the rotation in horizontal space, and Theta is basically the rotation in the vertical space. Okay. Other examples of directivity is in this case here is a horizontal directivity. We can change the view. Let me set the coordinates, the zoom factor maybe to actually this is in the system, I can't change that, but let me just change that in the project. So here we have a horizontal directivity, so we have an increase 0 dB to the front and a tapering down into this area. Now the horizontal directivity is only in the horizontal direction, so it doesn't matter what the elevation of the receiver relative to source is. If you have a receiver in a certain direction, whatever that angle is, it will apply that correction. In this case, and like 45 degrees, it would be a 0 dB, and let's say in negative or 135 dB direction would be negative 10 decibels. All right. Now you can take this directivity, use that for example, the building vertical. So here we have a vertical 2D directivity. So that would be for a source that is on top of a roof. So that could be used. But you could also take that and rotate it around. So you can make that into a rotational symmetric source. And here's the raw data, or the values in the angle from 0 to 180. So it's basically one quadrant. And then here all the other angles would be copied from that. So it's basically rotational symmetric. So we basically define from 0 to 180, and then the program duplicates it down in this way and then rotates it around 360 degrees. Now this input is frequency independent. So if we define it for octaves or third octaves, then of course we get additional inputs that are required at that point. So what happens if you have, for example, a loudspeaker CLF, common loudspeaker format file? What can you do then? A common loudspeaker format file could be something that you can import into the library. So if we go and open up a source or emission library, what you can do here is you can import, file, import. Okay, so we can import a CLF file. I have a JPL of different CF2 files, which are common loudspeaker format files. So let me open up this CBT100LA music wide, and it opened up the directivity. It opened up all the details about the speaker, where the data came from, and then here we can look up the directivity. So we look in the directivity. So here we have the directivity pattern here at 100 Hertz. So here we can see this is in 5-degree steps. So fairly omnidirectional. Let's go at like higher frequencies. So here we have like almost like a little donut. Let me turn on the planes. All right. So here we can page through the directivity patterns. So again, the green is the horizontal slice. The blue is the blue is the horizontal. The green is the vertical slice. And in here we can kind of see all the directivity. All right. And that's kind of how you again import a CLF file. Now, when you import the CLF file, then and here you have the frequency spectrum. So here we can again change the spectrum to the spectrum that you want to have for your source. And then again, it's a question of how do you position that source, right? So to position that source, I go back to the Geo-Database. And in this case, I'll just open up one of these situations. And then I'll add a point source. Let's say, let me put in a point source right here. And we use the same directivity or the spectrum that we just imported right here. And then here we have now, because the source has a directivity, we have an additional directivity tab here in the source input. And then here we can make changes to that source directivity. Let's put the source maybe 15 meters above the ground. And then here we can, let's say we go to maybe 2 kilohertz. So here we have the horizontal rotation. Here we have the vertical rotation and the roll. So in this case, in terms of the vertical, so this is primarily radiating upwards. So let's change that. So let me change that to 0. So now we have the source basically pointing sideways, and in here, or basically horizontally, it's radiating right now horizontally, and it radiates in basically into the east. And then we can rotate that again. So let's say we are rotating that to 90 degrees. So now this source is pointing to the north, right? So here we can see it's now pointing to the north. If you want, we can point it a little bit downwards towards the ground. All right, so if we had like for example a speaker setup around a facility to provide like public announcements, we could have speakers on the outside of the field, and we could have speakers that basically cover the different areas. And so in this case, we could rotate the directivity however we want in terms of the horizontal orientation. And then here in the center, in terms of the vertical rotation or the vertical pitch of the speakers. So in this case, we would maybe go down 30 degrees from the 15-meter pole. And with that, we are covering a wider range close to the speaker. All right. Now this is done now, of course, for all frequencies. So here we can look at each of those frequencies, how that pattern looks. And of course, the lower we go in frequencies, the more omnidirectional the whole thing becomes. So the directivity, of course, is very directional at higher frequencies. So let me show a couple other examples. Here's a stack. So here, this is a stack with a 3D directivity. This is a rotational directivity again. So this is a rotational directivity around the point source. So here's the frequency. And to look at the individual frequencies, we can go in here and get an idea. And again, we can turn on the grid, we can turn on the different planes. All right. For example, if I wanted to just generate a very simple directivity, we could add a new element, and we could just say this is a simple stack directivity, and this is rotational symmetric every 10 degrees. We want it in octave bands 31 Hertz to 8 kilohertz. And the values in the angles, we could put in like 3D, let's say 3, 2, 1, 0, and then we have -2, -5, -6, -10, -15, and then -20, and then we'll just keep the 20 for the rest. And then here we can kind of get an idea of what that looks like. So it's pretty omnidirectional. Of course, some decay here at low frequencies, and then of course we can go to the next frequency and so on, and copy the data there. All right. So if we, for example, at 1 kilohertz, we maybe have like 6, 4, 3, and then we have maybe at this point -20, -25, -30, and something like this here, and then there's your directivity. All right. Now, with any of these directivity patterns that you put in, we also want to make sure that the total of the directivity corrections is again sums up to 0 decibels. So SoundPLAN has the a correction function right here, and so here we can normalize the directivity. So in this case, I only have these 2, so I can normalize that, and then it normalizes them to 0, so that the total is back to 0. So here, in this case, for 31 Hertz, it would start with +10, and then all the other additions, so that the total of all the direction would again equal to 0 dB in terms of the sound power definition. All right. For 1 kilohertz, we get 9 to, again, -26 dB. Thank you for listening. I hope this video had some information for you. If you have any questions, please feel free to leave a message in the comment section.